Good afternoon. In today's session, we are supposed to study about the differential pulse code modulation. In previous session, we have seen about the pulse code modulation system. It is the method of converting analog signal into a digital form. If we are supposed to transmit the data, that will be analog. So here we are firstly doing that analog signal converting into a digital, and then we are transmitting. So we can do different method to transmit that analog into a digital format, like pulse code modulation, differential pulse code modulations, delta, adaptive delta modulations, and the linear predictive system, linear predictive coding. Pulse code modulations, delta modulations already we have seen. Now we are supposed to study about the differential pulse code modulations. What is the necessity of differential pulse code modulations? Because when we have seen about the pulse code modulation, at that time we are saying that is the digital pulse modulation technique, or we can say it is a simple technique in which we are sampling same information, we are quantized to one of other L levels, and each quantized level we are doing digitally encoding into a V bits. It means what? When we are converting analog into a digital format, at that time we are doing the sampling, we are doing the quantizing, encoding, decoding. So here when we are using the pulse code modulations, at that time PCM is not really efficient because it will generate many bits. So it will taking up lot of bandwidth. So can we improve on this? Yes, absolutely we can improve. How? If we are having the signal and we are varying that signal slowly, then we exploit this by using the difference between two adjacent samples. So we can say that sampling process as a differential pulse code modulations. So when we are supposed to study about the differential pulse code modulations, it will have improved version on the pulse code modulations, because here we can simply slowly vary the signal. So this will form the basis of differential pulse code modulations, because here we are varying the signal, and that will be done by taking the difference between two adjacent samples. So here let consider signal M of k be the kth sample reading of the signal sample signal M of t. So here if we are taking these two samples, we can take the difference between two adjacent samples. These are nothing but the kth sample we are taking as a M of t. So we can take the difference between these two adjacent samples as d of k equal to M of k minus M of k minus 1. Instead of transmitting, we transmit d of k. It means what? Here instead of transmit M of k signal, that is the kth sample of the signal M of t, we can transmit here that difference between the two adjacent samples, that is nothing but d of k. So at the receiver side, knowing d of k and the previous sample M of k minus 1, the previous one, it will allow us to construct the value of signal, that is nothing but M of k. So how do we will get benefit from this? Because most of the times the sample of the information signals are correlated with each other. So there is a lot of redundancy in the signal, meaning they will have similar information that will be resides in two or the more samples which are adjacent with each other. For example, if we are sampling the voice signal at a rate that will be greater than Nyquist rate, we can say adjacent samples do not change much when we are saying about the voice signal. So if we use the PCM for transmit that signal, we will be transmitting more redundant information. So if we have a signal which has redundancy in it, we can predict its future value from its past value. So here we can use, instead of pulse modulations, we can use the differential pulse code modulations instead of transmitting encoded version of the sample. we can transmit here encoded version of the difference between two adjacent or the two consecutive samples. So here we will have the benefit because the difference of the sample, successive sample, almost always it is much smaller than the full range of the sample values of M of t. Full range we are taking from the minus MP to plus MP. So here we can use this fact to improve upon the efficiency of the pulse code modulations because here we are predicting the future value from its past value. We are sending here instead of the original, here we are sending the difference between the consecutive values. So here it will give us efficiency over the PCM by requiring fewer bits as compared to the pulse code modulations. So here when we are using the pulse code modulations, at that time we can make use of estimate signal denoted by, if we are having the original signal M of k, we can say estimated signal, we can denote by M estimate k. So we can use here previous sample that will be M of t to make this estimate. Suppose we are taking M estimate as estimate of the kth sample, then difference will be M of k minus M estimate of k. So we are saying the difference as a D of k. So it is the difference D of k which we are supposed to transmit. So now we have said now about the transmitter side. Now we will see about the receiver side. What will happen? At the receiver side, we will get the channel, we will get the signal. That is nothing but we will get estimated signal. So we can say we will get here estimated signal M estimate k. We will get that from the previous sample. Then generate M of k by adding the received D of k value to estimated. Thus we will get the reconstruction of sample we will get here. Now what we are doing here? At the receiver side, we will determine the estimated signal. How? That is nothing but M estimate k. How it will get here? We will get from the previous value. So here we can generate the signal, that is nothing but original M of k, by adding the received signal, that is the difference value to the estimated. It means what? M estimate k plus D of k. So obviously you will get the value that will be original. It means what? M of k. So here we will get the reconstruction of sample iteratively. So we will get here that estimation. Now here what we are saying here, when we are supposed to use differential pulse code modulations, at that time we will get here M of t plus t of s, that will be equal to approximately M of t plus t of s dm of t upon dt for small t of s. So here we can say we will get here approximation of the k plus 1 sample. We will get the sample mk of n from the two prior sample. These are nothing but we are taking M of k and its adjacent M of k minus 1. So here we are doing the prediction. So here we will get, we can do ever better than this. In general we can take for number of signal that are nothing but M of k equal to A1 mk minus 1, A2 mk minus 2 up to An mk minus 1, that are nothing but equal to mq of k. It is nothing but we can say here the set of AI, these are nothing but the predictor coefficient. We are predicting. This is the predicted value of M of k. It is the nth order predictor if we are taking for the nth order. Note that input will consist of weighted previous sample. These are nothing but mk minus 1, mk minus 2, mk minus 1, k minus n. So we are saying that input is M of k and we are taking its output, that is nothing but estimated, M estimated of k. So here we can say we will get for first order prediction M estimated k will be mk minus 1. For second order M estimated k will be mk minus 2. So here we can say we will get the predicted value for the nth order prediction. We can do that prediction as we are saying linear predictor. which we are implemented with the transversal filter. You can see here we can use here predictor circuit. The predictor is the DPCM, differential pulse code modulations, transmitter and receiver, and it is the linear weighted sum of samples, and we can implement using the shift register as shown in this diagram. We are using here transversal filter, that is step delay line you will get here. And if we are calculating the signal to noise ratio, instead of pulse code modulations, if we are using the differential pulse code modulations, and if you are calculating the signal to noise ratio, you will get SNR equal to, you will get GP into 3L square PS. So we can say by using the differential pulse code modulations, we will get here prediction of gain, that is nothing but GP. We will get that prediction enhancedly if you are using the differential pulse code modulations. But what we are doing here, if you see in the differential pulse code modulation, here we are sending the difference between the consecutive. So it will suffer from the slope overload for fast varying signal, just like the delta modulations. As we have seen in the delta modulations, we are saying there we will get the noise. These are nothing but we will get the slope overload and the granular noise. So here also when we are using the differential pulse code modulations, it is similar with the delta modulation, except in delta modulation we are sending one bit, but here the DPCM system and delta modulations are similar, except in delta modulation we are supposed to use only one bit quantizer. There is a single delay element instead of the predictor filter, but here we can use the predictor filter. Thus delta modulation is one bit version of the differential pulse code modulations, but it will also suffer the same slope overload and the granular noise for fast varying signal, just like the delta modulation. So we can say differential pulse code modulations will also have the quantization noise that will be similar to the delta modulation and the pulse code modulations. If you see, we can see here the circuit, the block diagram for the delta pulse code modulation, differential pulse code modulations transmitter and the differential pulse code receiver side. When we are sending the data at the transmitter side, if we are taking input as a M of k, at that time if we are estimated by using the predictor, that is nothing but M estimate of k, so we can take the difference, that is nothing but D of k equal to M of k minus M estimate k. So we can say that we are supposed to quantize to the yield. So we will get here quantization error, that will be Q of k equal to, how will you get, dq of k minus d of k. You can rearrange equation, reconvert, and you can write in any form. So here we are saying we will get the predicted output that we are supposed to feed back to the input. So here we will get the predicted input, that is nothing but mq of k equal to, we will get mq of k plus dq of k equal to m of k minus d of k plus dq of k equal to, you can say m of k plus q of k. So here we will get the quantized version of the original, mq of k of the sample signal, original sample, m of k. So here at the receiver side, at the receiver output, which is the predictor input at the receiver side, we will get the value, that is nothing but quantized version. You will get mq of k, that will be equal to m of k plus q of k. Hence we are able to receive the desired signal plus the quantized noise, that is nothing but q of k. So it is important to note that from the difference signal d of k, it is much smaller than that of the noise which will associated with the original sample signal m of k. So here we can use the differential pulse code modulations. So here we are supposed to study about the differential pulse code modulation signal to noise ratio. Is it better than the pulse or not? How much better is the DPCM with regard to the signal to noise ratio? as compared to the pulse code modulation. So here, to determine these, we are defining MP and DP as the peak amplitude of the original signal M of t and the differential signal D of t. Assuming that the same number of steps L for both, then quantization step, how we can denote? We are denoting quantization step by delta. In the DPCM is reduced by the magnitude dP by MP, because here instead of that signal, instead of that sample signal, we are transmitting the difference. So here that quantization step will get reduced by the dP by MP. So here the quantization noise we will get, that will be proportional to the delta square minus quantization noise. Power, it is reduced by dP by MP square. So here we are saying SNR will get increased by MP by dP square. So maintaining the same SNR, we are supposed to reduce the number of peak. If we are supposed to reduce the signal ratio, we are supposed to decrease the number of peaks. At that time only we will get the reduced signal to noise ratio. So here if we are saying one example, you can see the AT&T telephone system sometime operate 32 kilobyte per second, or it is operating 24 kilobyte per second when using the differential pulse code modulations. We are supposed to initially design that system which will take 64 kilobits per second data rate. At that time only you will get the same signal to noise ratio as compared to the pulse code modulation. Adaptive differential pulse code modulation we will see in the next session. Thank you.